We're very happy to have Dragan Masulovic from University of Novi Sad here today, talking about dual Ramsey properties for classes of algebras. Please, Dragan.
Thank you, Peter. Thank you very much. I am really happy to have the opportunity to talk at this seminar. So let's start with the classical result, which is known as the finite Ramsey theorem for sets at the moment. This is nowadays high school mathematics, and basically what it tells us is that for every number a and b, every natural number a and b, and every number of colors k, there is a natural number c such that c is Ramsey for b, a, and k, and this arrow has the following meaning. For every c element set c, so we take a finite set capital C with lowercase c elements, and for every coloring chi of a element subsets of C with k colors, there is a b element subset B of C such that all a element subsets of B are colored by the same color. This is a well-known, famous result, and this is one of the standard renderings of this result. However, there is another interpretation of this result, and this is the same result in a different language. Now, we can just think of, actually, there is an equivalence between k element subsets of an n element set and embeddings of a k element chain into an n element chain. So instead of working with sets and subsets, we can work with embeddings of chains and get the same result. This seems a trivial switch of the language, just a switch of the language, but it enables us to go one step further. And this step was made in the 1970s, when somehow they suggest that we can also speak about Ramsey properties for classes of structures, not only integers or sets, finite set, but also classes of finite structures. So the definition, the corresponding definition is this one. A class K of finite structures has the Ramsey property if the following holds. For all A and B in K, these are finite structures now, such that A embeds into B, and any number of colors, lowercase k, there is a structure C such that C is Ramsey for B, A, and K. Now, this arrow, this notation has the following meaning. Now, we say that C is Ramsey for B, A, and K if the following holds. Let A, B, and C be the substructures, and let K be the number of colors. Here we have 3 colors. And then this relationship holds if for every coloring of copies of A in C with K colors, so this binomial notation now means copies of A in C. So no matter how we color copies of A in C with K colors, there is always a monochromatic copy of B. So there is always a copy of B such that you can think of this as generalized points. Points of B that look like A are colored by the same color. Okay, and alas, most combinatorially interesting classes of structures do not have the Ramsey property. That was a huge disappointment in the 70s. So you start from a very important combinatorial result. You try to generalize it to structures, and it seems that we are going to get a meaningful generalization, and then everything fails. So there are 2 ways to actually rectify the injustice. In the early 70s already, when the original definition failed, the situation was rectified by adding more structure. So we can add more structure, and I will show examples in the following slide to get the Ramsey property. Nowadays, for some reasons, because Ramsey property has been connected to topological dynamics at the end of the 20th century, beginning of the 21st century. So because of the implications it has on the dynamical side of the phenomenon, these are now called pre-compact Ramsey expansions. And this term was suggested by Lionel Nguyen-Van. So the first approach is simply to add more structure. And the second approach is to relax the Ramsey property. Okay, so how do we enforce the Ramsey property by adding more structure? We usually add some linear orders. For example, the class of all finite graphs does not have the Ramsey property. But if you add all possible linear orders to all finite graphs, we end up with the class of structures which has the Ramsey property. Analogously, finite partial orders do not have the Ramsey property, but if you add all possible linear extensions to finite orders, we end up with the class of structures that has the Ramsey property. And the same goes for equivalence relations. The class of all finite equivalence relations does not have the Ramsey property, but if we add convex linear orders, we end up with the class of structures with the Ramsey property. And probably the most prominent result in this early stage of structural Ramsey theory is the Nash-Ettil-Rodel theorem from the late 1970s, which says that if we take a class of linearly ordered finite structures, so see, we need a linear order somehow to fix the order of the elements, to make the objects rigid. And if you make the object rigid, then the Ramsey property starts working. That's the moral of the story. If we take a class of linearly ordered finite relational structures of the same type, defined by a finite set of forbidden substructures. So Nash-Ettil-Rodel denote this class by form F. Then this class has the Ramsey property. This is a well-known statement nowadays in structural Ramsey theory. Another point of view is to relax the Ramsey property, and this is important for what I'm going to talk about afterwards. So yes, I've forgotten to mention that probably the first 20 to 22 minutes of the lecture, of the talk, I will be speaking about Ramsey phenomena, just to motivate the strange things that I'm going to use, and to try to somehow explain why I'm so excited about the result I'm going to speak about. So another way of rectifying the injustice is to simply relax the property. So instead of looking for a monochromatic copy of B, we can start looking for a copy of, we can allow more colors inside, but in a structured and prescribed way. These are called Ramsey degrees. Originally, it's the idea that comes from Fouché. Actually, Stevo Todorcevich once told me that it was not Fouché, it was years ago, but somehow Fouché was the first one to recognize that these numbers that we are going to call Ramsey degrees are actually posing as important parameters of the section. So nevertheless, we say that the class K of finite structures has small Ramsey degrees if for every A in K, there is a positive integer T. So you give me a finite structure, and I give you an integer T that depends only on that finite structure and nothing else, such that C, for every B, there is a C, which is Ramsey for B, A, K, and T. This means the following. Now, again, no matter how we color copies of A in C with K colors, let's say 4 colors this time, there will always be a copy of B, which is not necessarily monochromatic, but it has at most 2 colors. So the copies of A sitting inside this particular copy of B will always be colored by at most 2 colors if the Ramsey degree of A is 2. And surprisingly, in 2016, Andy Zucker proved that the 2 approaches are equivalent. An amalgamation class of finite structures has finite Ramsey degrees if and only if it has a precompact Ramsey expansion. It's the same thing. And actually, it's a very important result, because one of the most important hypotheses in structural Ramsey theory is that actually every class of structures has some Ramsey property. Every amalgamation class, of course, of finite relational structures has some Ramsey property, has finite Ramsey degrees. So from the situation where we were really desperate that no class of structures has this very strict Ramsey property, which is indeed the case, if we relax the notion and look for precompact expansions or small Ramsey degrees, which is equivalent, the same thing, we end up with the hypothesis that every amalgamation class of finite relational structures has a precompact Ramsey expansion or small Ramsey degrees is the same thing. So this is a very important hypothesis, and many mathematicians are actually working on this hypothesis and trying to prove it. So it seems that Ramsey phenomena are ubiquitous. That's the moral of the story. Now, another class of phenomena are the infinite Ramsey phenomena. The infinite Ramsey theorem is a Ramsey theorem that speaks about coloring substructures, finite substructures in a countably infinite structure. So actually, an infinite Ramsey theorem says that for every finite chain n and every number of colors k, we have that omega. Omega is the chain 0, 1, 2, 3. It's the first countable, the first infinite ordinal. Omega is Ramsey for omega n and k. Okay, so it's just the usual infinite Ramsey theorem. We color subsets of omega, n element subsets of omega with k colors, and then there is a subset of omega, an infinite subset which is monochromatic. Now, again, a formulation in terms of chains is important because it allows for generalizations. And of course, this result was generalized to cardinals already in the 30s by Sierpinski and those very important, people in set theory. But on the more combinatorially interesting side is results from the late 60s and early 70s by Galvin, Laver, and Devlin, who tried to take a look at Q, the rationals, the chain of the rationals. And Galvin proved in 1968 that somehow the chain of the rationals does not have the Ramsey property. However, Devlin then spotted in 1979 that, for every finite chain, there is an integer t that depends only on that chain, such that no matter how we color copies of n in Q, the chain of the rationals, with k colors, there will always be a copy of Q inside, which has at most t, which sees at most t colors. Now, recall that this t depends only on the finite chain n that whose copies we are coloring, nothing else. So the least such t is referred to as the big Ramsey degree of n in Q. Big because we now consider we color copies of finite structures in an countably infinite structure, and then this result about rationals was generalized to arbitrary structures in the famous Kekris-Pestov-Tudorcevich paper in 2005. Okay, so these were finite and infinite Ramsey theorem and their generalizations that lead to the notion of Ramsey degrees, small Ramsey degrees in the finite case and big Ramsey degrees in the countably infinite case. Of course, there are some results, sorry, yes. So Ramsey's theorem can be expressed as follows. Every finite chain has degree 1 in omega. Galvin and Devlin's result can be expressed as follows. Every finite chain has a finite degree in the rationals. And this degree has been computed. We know the exact number, but it's not relevant for this talk. It was Sauer who proved in 2006 that every finite graph has a finite degree in the Rado graph. And it was Dobrinin who then generalized, actually, not generalized, but actually expanded this result to show that every finite Kn-free graph has a finite Ramsey degree in the Hansen graph Hn, the universal Kn-free graph. And last year, Jan Hubička proved that every finite poset has a finite Ramsey degree in the random poset. And interestingly, there is an analogon of the Neshatil-Rodel theorem. It was proved by Andy Zucker 2 years ago, which is that if K is a class of finite relational structures of the same finite binary type, defined by a finite set of forbidden substructures. So again, it's a form F, where F is finite. And if L is a Froissart limit of K, then every finite structure from K has a finite big Ramsey degree in the Froissart limit of the class. All right, so these are the big Ramsey degrees. And as I said, so these are generalizations of the Ramsey property. In the finite case, we end up with small Ramsey degrees, and in the infinite case, we end up with big Ramsey degrees. Now, of course, there are dual results. And the finite dual Ramsey theorem was proved already in 1971. So basically, in terms of chains, it tells us that whenever A and B are finite chains and K is a number of colors, there is a finite chain C, such that C is dual Ramsey for B, A, and K. Now, this RS above the arrow means that we are coloring rigid surjections. So in the direct Ramsey result, the finite Ramsey theorem, we are coloring embeddings. For the dual Ramsey finite dual Ramsey theorem, we color rigid surjections. And now just quickly what the rigid surjection is. So we have two finite chains. That's, let's say, C. A is another finite chain. And then a rigid surjection works as follows. You take the first element onto the first element, always. And then the second element can go to the first element or the next element. So it can go here or here. So the third element of C can go to any of the previous two already occupied elements, or if it decides to go to a new element, it has to choose the first free element. So a rigid surjection is a surjection such that the image of every initial segment is always an initial segment. Okay, this is a rigid surjection. So a finite dual Ramsey theorem has a different formulation, but this one is convenient because it actually shows, it actually very easily demonstrates the categorical duality between the finite direct and finite dual Ramsey theorems. So in finite Ramsey, we color embeddings from A to C. In finite dual Ramsey, we color special surjections from C to A. So these are special injections from A to C. These are special surjections from C to A. And then in either case, there is a morphism such that in the direct case, W composed with all the embeddings. These are copies of A sitting in a particular copy of B, attain at most exactly one color. And in the dual case, a factor of factors, a special factor achieves at most one color. Okay, so I will not go into technicalities. The point of this slide is just to demonstrate that the dual Ramsey property indeed resembles what we expect to see when we speak about categorical duality. It will be important for several notions that I will introduce afterwards when I move to category theory. Just to introduce some facts. Okay, as for the infinite dual Ramsey theorem, there is a very deep result by Carlson and Simpson from 1994, which reads as follows. So for every finite chain and N and every number of colors K, we have that omega, the chain 0, 1, 2, 3, and so on, is dual Ramsey for omega N and K, but this flat symbol here denotes that we have to consider Borel colorings. So for every Borel coloring of rigid surjections of omega into N, there is a rigid surjection such that this set is monochromatic. So in the direct Ramsey theorem, infinite Ramsey theorem, we are coloring just arbitrary embeddings of N into omega. And in the dual case, we have to resort to Borel colorings because there are too many surjections. And then using the axiom of choice, you can always construct a counterexample very easily, straightforwardly. So we need structured colorings. And one of the good ways of structuring such colorings is to consider Borel colorings. All right. So in this short overview of Ramsey phenomena, we've seen that there are many examples of direct Ramsey phenomena in relational structures. So linearly ordered graphs, partially ordered sets, post sets, equivalence relations, metric spaces with linear orders. So basically, you take any relational structure, add somehow some kind of reasonable linear ordering, and you'll end up with the Ramsey property. Finite Ramsey degrees, infinite Ramsey degrees, everything is fine for relational structures. However, in the case of algebras, there are only a few examples. It's usually semi-lattices or unary algebras which somehow resemble relational structures or can easily be turned into relational structures. On the other hand, if you take a look at the dual Ramsey phenomena, for relational structures, there are only a few examples. They usually just examples about chains. Some kinds of chains have dual Ramsey properties. And actually, in this talk, I would like to show that it seems that algebras, universal algebras, are a natural rich natural setting for dual Ramsey phenomena. I will now demonstrate that if we go to, if we consider universal algebras, almost everything has a dual Ramsey property. Actually, more specifically, I will discuss two results. The first one is the following. Let omega be an arbitrary algebraic language, no restrictions, and let V be an arbitrary non-trivial variety of omega omega algebras. Then I'm going to demonstrate very briefly and very sketchily, in a very sketchy manner, that the class of all finite algebras in V has small dual Ramsey degrees. Okay, so you take a variety, any non-trivial variety, and consider only finite algebras inside. This class of structures has small dual Ramsey degrees. Of course, the corresponding morphisms are epimorphisms. In the direct Ramsey, when we speak about the direct Ramsey property, we always consider some embeddings. And when we speak about dual Ramsey properties, we always consider some surjective maps. And the most natural class of surjective maps are epimorphisms in this context. Okay. And as a corollary, I mean, this is not a corollary, it's more a remark. Just plug in your arbitrary variety of algebras and you'll get, non-trivial variety, and you'll end up with a class of algebras with the small dual Ramsey degrees. What's particularly interesting is that as a trivial consequence, finite groups in an arbitrary non-trivial variety of groups have small dual Ramsey degrees. Small dual Ramsey degrees. It's an open problem, and we don't know at the moment whether the same is true for the direct Ramsey property. If you take the class of all groups, all finite groups, does this class has any kind of Ramsey property? Let's say small Ramsey degrees. We don't know. That's a very important open question. However, in the dual context, everything works straightforwardly. So this comes as a straightforward corollary of a more general result, of course. And then the same holds for arbitrary variety. Now, another result considers the big Ramsey degrees. Now, let omega be an arbitrary countable algebraic language. So why countable? Because I'm going to consider Borel colorings, and I will have to go through, I need a set of terms to be countable to be able to work with Borel colorings, countable intersections of certain sets. So that's why we need the language to be countable. And then take V to be an arbitrary non-trivial variety of omega algebras. Then basically every finite algebra in this variety has a small dual Ramsey degree, has a finite big dual Ramsey degree in the free algebra on countably many generators with respect to Borel colorings. So if we consider only Borel colorings, every finite algebra has finite big dual Ramsey degree in the free algebra on omega generators. And actually we can estimate the degree. It's n times n factorial where n is the size of the finite algebra. So this estimate is very rough, but interestingly, we can actually provide an estimate of this Ramsey degree. And of course, this is a straightforward corollary. Just plug in your favorite variety of algebras, and we'll end up with an infinite Ramsey phenomenon. Now, let me say a few words about the proof strategy. So, my favorite strategy for proving Ramsey properties is sketched here. If I want to prove a new Ramsey statement, my point of view is actually to move to category theory. So we usually start from a well-known Ramsey statement, and this well-known statement is, let's say, the Graham-Rothschild theorem, or the finite dual Ramsey theorem, or the Carlson-Simpson theorem. We start from a well-known Ramsey statement and turn it into a categorical statement. So we'll move to category theory, because as I will try to demonstrate in the remaining 15 minutes or so, it turns out that Ramsey property is a genuine categorical property, and we can use the machinery of category theory to reason to get really significant results about the Ramsey property. So we take a well-known Ramsey statement, turn it into a categorical statement, then perform some categorical juggling, end up with a new categorical statement, which then can be reinterpreted as the new Ramsey statement. And this proof strategy will be applied to show both of the results that I mentioned a few moments ago. So the first thing to do is to somehow reinterpret the structural Ramsey theory in the language of category theory. And this goes straightforwardly. So we say that C is Ramsey for B, A, K, and T if every coloring of morphisms from A to C with K colors, for every coloring, there is a morphism from B to C. So it's an arrow that tells us which particular copy of B in C will be the oligochromatic one. So there is a morphism from B to C. So the pointer to this particular copy of B in C such that this copy of B attains at most T colors. So it's a straightforward generalization of the combinatorial statement that we've seen a few slides back. And then we say that the category C has the Ramsey property if for any number of colors K and all A and B, which are objects in C, there is an object in C such that C is Ramsey for B, A, and K. For the Ramsey property, we take this number of colors to the degree to be 1. And as motivated by this slide with the finite Ramsey property and finite dual Ramsey property, it goes straightforwardly. It's obvious that this makes sense. We say that C has the dual Ramsey property if the opposite category has the Ramsey property. So this is psychologically very important because working with dual Ramsey property is usually hard. Everything is backwards. But then we can, by moving to categorical reformulation of the Ramsey property, we can actually work with the direct Ramsey property in mind and obtain dual Ramsey property by simply performing this operation, which moves from a setting to the opposite setting. You just move to the opposite category and end up with the dual Ramsey statement. Okay, and then we introduce small and big Ramsey degrees straightforwardly. These are just straightforward generalization. A small Ramsey degree of A in a category C is just the least integer, the smallest integer S, such that C is Ramsey for B, A, K, and S. This arrow actually assumes several quantifiers, so that for every B there is a C, for every B and every K there is a C, and so on. Okay. Or infinity if no such S exists. And then we can introduce the dual small Ramsey degree of A. It's just the Ramsey degree of A computed in the opposite category. So formally, that's the same thing. Of course, combinatorially, things are significantly, essentially different. So this is convenient for introducing notions because I can always say a dual notion is introduced in the same manner, but just in the opposite category. But combinatorially, of course, things change significantly. And of course, big Ramsey degrees are introduced analogously. Now there is a technical glitch. Or it's not a glitch, sorry, there is a technical thing. So since we have to work with Borel colorings, because I am going to use the Carlson-Simpson theorem to piggyback on that to produce the result about the big dual Ramsey degrees in varieties. So our category C of objects has to be enriched over top, the category of topological spaces. This basically means that Hom sets are topological spaces and the composition is continuous. That's it. And in this setting, we can speak about Borel colorings because we have now Hom sets are topological spaces. So there is a perfectly valid notion of a Borel partition of a set of morphisms. And then we can introduce the big Ramsey degrees and the dual big Ramsey degrees straightforwardly. So the big Ramsey degree with respect to Borel colorings of A in F is just the least integer S such that this is the case, or infinitive if no such integer exists. And the dual big Ramsey degree with respect to Borel colorings is the same thing computed in the opposite category. Okay, this is just the categorical reinterpretation of all the notions, and it's straightforward. So now comes the construction. I want to work with varieties of algebras, and one reasonable way to do it is to use the available categorical machinery to speak about free algebras and varieties of algebras. And this machinery needs the infrastructure, which is called a monad. So a monad in a category C is a triple, where T is a functor. Mu is called the multiplication. So T is an endofactor. It takes C to C. Mu is the multiplication. It's called the multiplication. It's a natural transformation from TT to T, such that this diagram commutes always. I will not go into categorical technicalities. And eta is a natural transformation which takes the identity functor to T and makes this diagram commute. Okay, so the only monad that we will need in this talk is the term algebra monad. So I'll perhaps demonstrate these ideas in case of the term algebra monad. So let T be the functor which takes the category of sets onto itself and takes a set X, a set of variables. We think of X as a set of variables to the set of all omega terms over X. Omega is a fixed algebraic language, of course. So you see, a monad gives us a way to provide a set, to turn a set into a structured set. So you take an unstructured set X of variables, and you end up with a structured set terms over X, omega terms over X, where we already can perform certain actions. So eta just takes X to T of X by taking a variable X as an element of the set of variables to the corresponding term X. And mu is just the substitution. So we take a term built on terms over X. So we take an element of this form, a term where for each variable we substitute a term and then just perform the substitution. So in the term algebra monad, mu is just substitution. Okay, and eta is the trivial map which takes X to X. And now with this infrastructure at hand, we can say what a T algebra is. If T is an arbitrary endofunctor, a T algebra is just a pair A alpha, where alpha is a morphism from T of A to A. And F is a homomorphism between T algebras if this diagram commutes. This is exactly what we speak in universal algebra, just in the different language. Instead of considering a signature and then building and then algebras as a structured sets where the structure is the signature, we simply just throw all the terms of A in a bag and just tell how an algebra evaluates terms, and that's T of A. Alpha is precisely an evaluation map in a particular algebra. So it's the same thing. We are speaking about the same objects, but using a different language. So this is how we treat algebras in category theory. Now, if T is a monad, if T is more than an endofunctor, then there are special kinds of algebras called Eilenberg-Moore algebras. And these are algebras with two additional properties, which I will not discuss in detail. So we can build the category of Eilenberg-Moore algebras, T algebras, where objects are the algebras and morphisms are just usual algebra homomorphisms. And the issue that we now have with this construction is that I want to work with the Dual Ramsey property, where morphisms are some surjective maps. In this context, epimorphisms. So this here is a standard take on algebras in category theory. The problem that I have is that eta is always an embedding, so I cannot have eta in my language. So monads are just too structured for what I would like to get. Functors are too unstructured. Full monads are too structured, and I cannot implement eta because eta is usually an embedding of X into T of X. And the only morphisms I have at my disposal are epimorphisms. So the main trick is here to just get rid of eta and speak about half a monad. It's just a functor and a multiplication, and then repeat the entire construction without the eta. So we call such objects weak Eilenberg-Moore algebras. So they are built for weaker infrastructure, and we require less for each algebra. Nevertheless, we end up with the category of weak Allenberg-Moore algebras, and morphisms are again homomorphisms between T algebras. And then the major idea for the proof of the results I mentioned is this very obvious but unfortunately useless fact. So if T is a monad and C has the dual Ramsey property, then the Allenberg-Moore category has the dual Ramsey property. So the category of EM algebras for the monad has the dual Ramsey property. This is straightforward because right adjoints preserve the dual Ramsey property, and this construction was actually made to prove that every monad can be produced by an adjunction. So right adjoints preserve the Ramsey property. That's easy to show, and EM comes at the appropriate side of a right adjoint functor, and that's it. So this is a straightforward statement with very easy proof. However, it's a motivating statement because we can, using the same idea, prove a less trivial and more useful statement for algebras, for weak EM algebras. And this basically tells us that if C is an endofunctor and M is a multiplication, and if C has the dual Ramsey property, that you see every full subcategory of this category, which contains all the free algebras, also has the dual Ramsey property. So this is the starting point for our result. This proof is relatively easy but technical. We have to use an unorthodox notion called pre-adjunctions, a pre-adjunction between the two categories, and then so it's rather technical but easy. Nevertheless, that's the starting point. So we can transport the Ramsey property from a category C to the category of weak Allenberg-Moore algebras, and moreover to every subcategory of this category which contains all the free T algebras. And now let me just give you a quick sketch of the proofs of the two statements. So if omega is an arbitrary language, algebraic language, and V is an arbitrary non-trivial variety, we claim that the class V-fin, finite algebras in V, has small dual Ramsey degrees. The proof is pretty lengthy and pretty technical, but these are the major steps. So we start with the dual Ramsey, finite dual Ramsey, we start with the finite dual Ramsey theorem, which in categorical terms tells us that the category of well-ordered finite chains and rigid surjections has the dual Ramsey property. And then we use the free algebra monad and upgrade it from set to the category of finite chains. This is a technicality, but it can be done. I can take okay, so it's not a monad. We work with half a monad. We get rid of eta, and we take the multiplication and the functor and upgrade from sets to chains, and thus form the weak Allenberg-Moore category for this, well, half a monad. Okay, now these are well-ordered algebras and rigid epimorphisms, and this has the Ramsey property. Okay, then, okay, using a pre-adjunction, a technicality, we prove that for every finite ordered A and B, this countably infinite object, the ordered free algebra over omega generators, sorry, it's not necessarily countably infinite, it can be very infinite, okay, because omega is an arbitrary language, sorry. So this infinite object is dual Ramsey for finite A and finite B. Then we use a compactness argument to go down from this infinite object to a finite C and get the dual Ramsey property for ordered structures. And then we perform some arithmetic with dual Ramsey degrees. It's really an arithmetic to get rid of the linear orders and prove that unordered algebras, that what we actually want to get is that the class of usual algebras with no extra linear ordering, no infrastructure, has small dual Ramsey degrees. So you see, the passage is that ordered structures have the Ramsey property, degree 1. Unordered structures do not have the Ramsey property anymore, but have a finite degree. Okay, so there is a connection between the Ramsey property of ordered structures and finite degrees of unordered structures, and the arithmetic that I mentioned before between Ramsey degrees is the connection between the two. But I will skip the technicalities. Okay, so that's the first result. And we use a similar idea to prove the second result. Now, if omega is a countable algebraic language and V is a non-trivial variety of omega algebras, then we can prove that every finite algebra in V has the finite dual big Ramsey degree with respect to Borel colorings in the free algebra on omega generators. And actually, we can estimate the size of this big Ramsey degree. So first, all the categories I'm working with are enriched over the top in the obvious way. So you have surjective maps from an countable infinite object into a finite object. So you can just take the discrete topology on the finite object, which is trivially compact. So by the Tikhonov theorem, the space, the set of all maps is a compact topological space, and that's how we enrich. I think that's the straightforward, easy way to get topology on morphisms. And then we use the infinite dual Ramsey theorem, which tells us that every finite chain has a degree 1, big dual Ramsey degree 1 in omega in the category of well-ordered chains and rigid surjections. Then we use again the Allenberg-Moore construction to piggyback on that and end up with the result that in the category of ordered algebras and rigid epimorphisms, the degrees are already finite. And then performing a similar arithmetic enables us to go from big Ramsey degrees on ordered algebras to big Ramsey degrees on unordered algebras, which is actually what we want. So there are many technical steps, but this is basically the idea. So you see, we start from a well-known Ramsey statement, piggyback on that, massage the statement as much as possible to turn it into what we would like to get, and then end up with a statement on ordered structures, and then perform some more trickery. This is just combinatorial trickery to get rid of linear orders, increase the degree, but keep it finite. And we end up with finite degrees, small in the first case and big in the second case. And let me conclude with a few open problems in the remaining 35 seconds. A very important open problem is this one, open problem 1. Does the class of finite groups have small Ramsey degrees? We don't know that. So finite groups, all finite groups, and the usual Ramsey property. This would be a very important, it will be very important to know whether this is the case or not. Another open problem is how we can, that's more an open problem for me than for the combinatorial community. So by dualizing this argument, we can prove various Ramsey properties for co-equationally defined classes of co-algebras for a co-monad. Okay, so it's relatively easy to perform the dual constructions. Now, can this be used in the real world? I haven't done this properly because I don't know whether I haven't found a reasonable application in the real world. But I would really like to somehow see whether co-equationally defined classes of coalgebras for a comonad do have some real-world appearance. We can use this dual point of view to strengthen some of Sokic's results about the Ramsey classes of unary algebras, and of course, it would be of interest to know whether there are more colorful classes of algebras that can fit into this setting. I'm thinking about that at the moment, but it's still work in progress. And finally, now when the comonads have been in effective use in functional programming community for quite some time, and coalgebras are natural models of computation. So coalgebras for a comonad are of interest in computer science community, and actually I'm very much interested to know what does it mean for a class of computational processes to have the Ramsey property. So this is also a thing I've been thinking about lately, and I believe that, I mean, maybe there should be some deep connection between the Ramsey property and computational properties that can be somehow expressed in this language of coalgebras for a comonad, but this is not in near future. Thank you very much.
Thank you, Dragan.